Hello everyone, welcome to the next video. I had a few comments about the quality of my videos, both the video and the audio. So went out and got myself a microphone, switched up the video software that I'm using, so you'll have to let me know if that makes any bit of difference or if you just don't really care. So the topic for our discussion today is on gas pressure. The vocab words that we're going to go over today are already in Quizlet, so you should be studying those already. Alright, let's jump into gas pressure. So when we're talking about gas pressure, what we're looking at are the forces caused by the collisions of the gas particles with the walls of the container. What we're trying to figure out is, or what we're trying to measure, is the number of collisions between the particles themselves. As of yet, we don't really have a way to measure that accurately, so all we can do is measure the collisions and the force of the collisions with the walls of the container, whatever it is, and really just a piece of the wall of the container that has the sensor. So we're looking at the frequency of those collisions and the force, how strong, how hard are they hitting the wall of the container. The units that we're going to use a force unit divided by the amount of area, right? How much force is being applied to how big of a sensor do we have? So we're going to get a ratio. In America, we tend to, the metric units that we use, newtons is the metric unit for force, and then meter squared is our unit of area. In America, we use pounds per square inch, or PSI. You might see that somewhere on a propane tank or on your car tire or bike tire or basketball. It says PSI. How much force do we want those gas particles to exert in that area, whatever we're talking about, meters squared, inches squared, whatever. The first is a device for measuring atmospheric pressure, so we're looking at the collisions in the atmosphere, not in an enclosed space, but in the atmosphere. Was first developed by Evangelista Torricelli, and I'm probably saying that wrong, it's Italian, during the 17th century is when he first developed his device for measuring atmospheric pressure. And here's a picture of him. And as I said, Torricelli was an Italian physicist and mathematician during the 17th century, worked with Galileo during the last 3 months of Galileo's life. Galileo was under house arrest because of some of the things he had published going against the accepted beliefs of the Catholic Church at the time, and Torricelli was one who worked with Galileo during the last few months of his life in his home, because that's where Galileo couldn't leave his home because he was under arrest. 2 years after Galileo died, Torricelli, following a suggestion from Galileo, invented this device that he used to measure atmospheric pressure, which he named a barometer. Baro meaning weight, meter meaning measure, so what he's measuring is the weight of the air, right? Measuring the weight of the air particles. But really what we know that he was measuring was not the weight, but the force that they were exerting through their constant motion. And here's a diagram of his first barometer, and what he did is he took a long tube. The one that he used was 4 feet long, so we're talking 1.2 meters long, so it's a pretty long tube. Filled it all the way with water, turned it upside down, and of course when you turn something upside down, the water's going to come out. Well, what he did, and we did something similar to this already, is he turned it upside down, but the opening was under the water. He put it in a dish, and so the water came down, but then it stopped, and he noticed that the water only came down a certain amount. Okay, well, he left it for a day or two and came back and noticed that the water level had shifted a little bit, either a little bit higher or a little bit lower. So he started thinking, what's going on here? You know, what am I seeing? And what he noticed was, is, if you think about it, the only forces acting on the water in this tube is you've got the air pressure pushing down on the water and the water pushing up in the tube. So and there's nothing up here. There is nothing up here in this it's a vacuum. There's nothing up there. There's no air. There's nothing. That's what a vacuum is. And so he started wondering, why would the water in the tube, why would the level change, go up and down? And what he realized was that he was measuring the water, the air pressure, the atmospheric pressure, and it would change based on certain weather conditions, right? When you've heard it on the news, when we have a high pressure or a low pressure coming in, that's what that means, right? And he noticed and calculated and published that the normal pressure due to the atmosphere at sea level can support a column of mercury, right? If we start using mercury, because we can use a shorter tube because it's more dense, we get air pressure that pushes the mercury up 760 millimeters. So just under 1 meter, right? About 0.7, well, it's exactly 0.76 meters of mercury. Torricelli originally used water, but because mercury is more dense, we switched to mercury. But now everything's digital, right? So we don't really use mercury anymore anyway. When we're measuring pressure, we have several different units that we use. I noticed, I mentioned before that the SI unit for pressure, or for force, is a Newton, and for area is a meter squared. So the SI unit for pressure is a Pascal, okay, which is defined as 1 Newton per meter squared. Sometimes you'll also see millimeters of mercury or inches of mercury here in the United States, but no one else uses inches, so millimeters of mercury. And that's going back to Torricelli's first barometer, right? How far does the air pressure, does the atmospheric pressure push mercury up into a barometer? So we call that millimeters of mercury, or mmHg. I'm going to skip down to this last one. So a torr, I hope you see, is named after Torricelli, who first invented the barometer. And the conversions from torr to millimeters of mercury is really easy, because 1 torr equals 1 millimeter of mercury. It's a 1-to-1. It's really simple. To make the math easier, sometimes we'll use atmospheres, okay, or ATM. And that's looking at the average atmospheric pressure at sea level and 0 degrees Celsius. That equals 1 ATM. So however much pressure we have at sea level, 0 degrees Celsius, that's going to equal 1 ATM. All right. So I mean, you can kind of see where this is going. We're going to need to be able to convert between these 4 different units of measuring pressure. And so we have 1 atmosphere, or 1.0 atmospheres, is going to equal 101.3 kilopascals. Notice that that's kilopascals and not just a pascal, so that's 1,000 pascals. So 101.3 kilopascals is 1.0 atmospheres. That equals 700 millimeters of mercury. And as we saw before, millimeters of mercury are the same as torr, and so that's also going to equal 760 torr. So that's what's going to be what we call our standard pressure. So if we have either of these conditions, 273 K or 0 Celsius, we should remember from our last video, those are the same thing. So if we have anything that's at 273 Kelvin or 0 degrees Celsius and is at standard pressure, 1.0 atmospheres, 101.3 kilopascals, 760 millimeters of mercury, 760 torr, right? That's standard pressure. That's what we call standard temperature and pressure, or STP. It's going to be very important that we remember this is STP. So standard temperature and pressure, 0 Celsius or 273 Kelvin, and 1 atmosphere, or any of these others that are equivalent to 1 atmosphere. That's our standard temperature and pressure. It's just a shorthand way of communicating the conditions that we have our gas. So let's go ahead and practice converting between these units. So helium balloons are filled with pressurized tanks. A new tank is manufactured at about 790 kPa, kilopascals. And this wants us to express this in ATMs. So we're going to need to convert kilopascals to ATMs, to atmospheres. So with our conversion factor, 101.3 kPa equals 1.0 ATM. Now there are several different ways to do this. I like to set up a ratio. If you have another way that you like to do it and it works for you, great, go for it, use that way. But I like to set up ratios. So here's the ratio that I'm going to set up. 101.3 kPa over something equals 1.0 ATM over something else. And what I'm going to plug into, so notice that these are my standard pressures, right? These are my standard pressures. This is my conversion factor. So now I'm going to plug in the numbers that I get from the question. So I'm going to put in 1790 kPa down here, and I don't know how much ATMs, that's what I'm trying to find out. And using cross multiplication and then division, I can find that my atmosphere, my pressure in atmospheres is 17.7. We'll round to three figures for most of our questions in here. So 17.7. And then it's actually 17.6 something, 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 but it rounds up to 17.7. All right, for our next practice, an experiment is performed at an atmospheric pressure of 758.7 millimeters of mercury. What is this pressure in kPa? All right, using our conversion factor of 760 millimeters of mercury is 101.3 kPa. I'm going to set up my ratio here. 760 millimeters of mercury over something equals 101.3 kPa over something else. Again, these are my standard pressures. And then setting up a ratio here, 758.7 that I get from the question right here. And then X at kPa, again, I don't know what my kilopascals are. That's what I'm trying to find. Using cross multiplication and division, I find that my pressure is just under standard pressure at 101.1 kPa, and that makes sense. If we go back, 760 millimeters of mercury is standard pressure. I'm at 758.7, so it makes sense that I would be just under standard pressure in kPa. Well, that is a crash course in pressure. Again, vocab is up on Quizlet. Make sure you're continuing with that. If you have any questions, be sure to either drop them in the comments or make sure you ask when you come back to class. Have a great day, everybody.